I can't hear you, Joe. That's what the book says, right? But why did we say a transducer was? That's good to read that. And that's what the book says, but the book is not exactly right. But a lot of people refer to the sensors as so a sensor is a transducer, but a transducer does not have to be a sensor. So that's what our sensors do. So a sensor is a transducer, but that's not the definition of a transducer. Um, so it's like saying a Ford is a car, but a car don't have to be a Ford, right? Even though people drive Fords, they think it's like Harley Davidsons, right? Harley driver says, well, Harley Davidsons are motorcycles and everybody else drives scooters, right? So, so a transducer is a device that takes energy in one form and converts it to another form, period. So a windmill is a transducer. The engine in your car is a transducer. So the engine in your car takes energy from gasoline and converts it into what? Into motion. So that's what a transducer is. So a transducer, a sensor definitely takes a physical stimulus and then converts it over to a electrical equivalent. So we got to stimulate these things, guys. It's just like your nerves, right? Your nerves. What does your nerves do? What do your nerves do? Takes a physical stimulus and converts it into an electrical signal so your brain can process it. That's what. So our sensors that we use on our manufacturing lines or our automated system, that's exactly what they do. They do exactly what your nerves do. And we was looking at different things that we actually sense, and we started a little bit out of whack with the book. So we started off with magnetic sensors, right? And what was the magnetic sensors that we looked at? What was the first one that we looked at? We looked at a reed switch, which is technically not a solid state sensor, but it's still a non-contact sensor. So we have two categories of sensors. We have contact and non-contact, right? Yeah. What was the first one we looked at? Proximity switch. So a proximity switch is a term that we use for it. So proximity switches are a category of sensors. So proximity switch is not a sensor, it's a category of sensors, right? You understand? Okay. It's just like we would say Ford is a category of vehicles. So they make but how many vehicles do they make? A lot, right? So that's what we're saying. Dodge would be a category of vehicles. Yeah. So, but what we're saying though is proximity means when we use the term proximity, we're talking about non-contact sensors, which means they do not have to make physical contact with what they're trying to measure. Okay. And so a reed switch would be a proximity sensor, and then a Hall effect, which is in the book, would be a proximity sensor. So a Hall effect is a solid state sensor. So that's the big difference in that a reed switch does not consume power because it's a switch, but a Hall effect does. So a reed switch is going to be a 2-wire sensor, and then a Hall effect is going to be a 3-wire sensor because it's got to be powered, right? You understand? Now in motor controls, if we were going to, let me get this. Have y'all had motor controls yet? You ever had motor controls? You had motor controls today. What was the symbol for a sensor in motor controls? Hmm. most of our sensors, except for sensors like limit switches, only provide one contact. We're waiting on PowerPoint. Resistance, right? And what's the other two? No, what three things can a sensor? So the sensor is going to take a physical stimulus, right? So over here we got physical, and over here we got electrical. So what I'm trying to do is what electrical signal can the sensor give us? We got three things, right? We got three things. Oh, thank you. Resistance. As soon as I spell resistance right, guys, I'm off on a tangent here. That's one of the words I should know. So we got resistance, then we could do what? Do current, and then what we could, the sensor could provide voltage, right? So those are the three things it could give us. Now I got thermistor. So what's the physical it's going to sense? Temperature, yeah. Let me go bring temperature in over here, and what are we going to get out of it? Thermistor. Thermistor. I'm looking for the electrical, guys. I'm looking for, it's going to take a physical stimulus and convert it into electrical signal. So what's it going to be? Is it going to be resistance, or is it going to be current, or is it going to be voltage? Thermistor. Resistance. Yeah. So a thermistor. I gave y'all as many hints as I could. So what this guy here is, it's going to vary its resistance with temperature. We have two. We have what we call a NTC, and the other one we have is a PTC. And what do you think that means? What do you think the N stands for? Negative, yeah. And what do you think the N stands for? And what does the T stand for? Temperature. Okay. And the C stand for? Coefficient. So find these things in your book and tell me what NTC and PTC stands for. So NTC means that the resistance goes down with an increase of temperature, and PTC means the resistance goes up with an increase in temperature. So what happens, though, is that the temperature that it measures, or the resistance to the temperature, so we'd be dealing with this, so it goes down. So this would be temperature, and this would be resistance. The curve looks like this, which means it's nonlinear. If it was linear, it would do what? What does linear mean? So if something linear, what does that mean? Anybody know? Well, its quantity varies in a straight line. No, that's not true. It's a good guess, though. So linear means it varies in a straight line. So if this guy was linear, if this was a linear device, then the line would look like this. It'd be a straight line, which means you could calculate that thing precisely. You know, if it had 10K, if it had 10K when it was at 0 degrees, and then it had, then it had 100 ohms when it was at, 60 degrees centigrade, then you can say, okay, what would it have if this was 0 and this was 60? Then if it was right there, by George, that circle would be 30 degrees centigrade or Celsius, because it's linear, right? You understand? So linear devices are real easy to figure out because they vary in a straight line. Thermistors are not linear, which means they don't change at the same rate. So it might change faster from 0 to 30 degrees, and then it kind of levels out, and then it's going to change slower the hotter it gets, right? You understand? So what we want to do is we never want to operate a thermistor over its entire range, because it would be what? Nonlinear. But if we come over here and operate it between a very small range like that, it appears to be linear, right? You understand that? So this is the way it works in your air conditioners, in your HVAC. So if you've got a digital thermometer, guys, how does it sense? What does it use? It uses a thermistor, right? So this is before I got my new one. This is my old digital thermostat. This is the first one I ever got, by the way. And it probably still works. This little thing right here with the blue dot on it, that's light dot, that's the thermistor right there. And of course, it's opened up to my house temperature, right? And it varies its resistance with what? With temperature. But we don't operate it over a wide range. What temperatures do your house usually operate between? Yeah, we cut mine down way down at night because I like to sleep in cool weather. So mine is like 65 to 73. And that's maximum. Well, you're talking about the range is so small that if we operate a thermistor over a real small range, then it means it's going to give us a really accurate measurement, right? Here we go. So you're going to look at the thermistor in the back. That's the little guy with the blue dot, and then of course it goes into a lot of electronics. Another thing we can do is we can use a thermistor. And if we know the ratio, of change, then we can compensate for the change with electronics. So we do have linear temperature measurements. We got an LM, I can't remember. I think it's a 32, and it's a 3-lead device. And this guy right here is a Celsius temperature sensor, and it is linear, because they compensate for the thermistor electronically, right? You understand? I think it's an LM33, I think. We can look them up. We got one of them over there. One of them does Celsius, and the other one does Fahrenheit. So one of them's calibrated for the Fahrenheit scale, and one of them's calibrated for the Celsius scale. These guys are linear. But how do they compensate for the thermistor? They do it electronically, right? We could do it with a computer program real easy. All we got to know is the ohms per degree, and then what we would do is we would look it up in a chart. So these guys are real cool, guys. This is the thermistor. Let me find my parts. Now, if I want to take a resistance and turn it into a voltage, so we know that resistance is real hard to deal with, right? So if I want to make temperature and convert it into a voltage, then what would we do? Resistance and convert it into a voltage, what would we do? We'll take a varying resistance, and convert it into a varying voltage. So here's my thermistor right here. And what I'm going to do is I'm going to come over here, and we'll see if we can get it to change. And I'm going to bring my meter into play. And I'm going to come over here and turn it on, and I'm going to put it on tones. And then I'm just going to measure across the thermistor. Okay. In fact, we can put it right here. And then I'm going to come over here and just touch it with my fingers. And you can see as soon as I touch it, sorry. As soon as I touch it, can y'all see that? I think we got a glare, guys. There we go. As soon as I touch it, the resistance starts going down. As soon as I let it off, the resistance starts coming up, right? You understand? So what would this be? Would it be a TTC or an NTC? Yeah, NTC, because the resistance goes down, right, when temperature goes up. So this is probably what they use in these little electronic thermometers that you come up here and you put in your mouth, right? But no, there they probably use a PTC, right? Because when your temperature goes up, you want okay. Well, that's not true. We'll see how we do this. But I want to take this. So it's real hard to send it's real hard to we can't transmit a resistance. So what I need to do is I need to take this change in resistance and convert it into a voltage. How do I do that? We did it with this guy right here, right? So we should be able to do it with that guy right there. What would I need to do? Yeah, we did it right here. We did it with our photoresistor. Did we play around with the photoresistor last class? Okay. So it changed photoresistor. So what does it change? It changes its resistance relative to what? To light. Okay. And we talked about these things are all over the place. This is what turns on lights at night, right? And turns them back on at days. This is the sensor that we use, and it's solid state. This is a solid state sensor. But what do I need to do, guys? I need to get something that varies a resistance, and then I want to convert it into a voltage. Nobody's got any ideas? I want to take something that generates a resistance, that changes its resistance with what it measures, and I want to somehow add another component that will make it give me a voltage that changes with resistance. You might have sort of the right idea. Well, no, that's what we're simulating. So the sensor itself is, but a rheostat, who turns a rheostat? You do. These guys are doing exactly what a rheostat does, but they do it with a physical quantity. So I'm not turning this thermistor. It's changing its resistance with temperature, huh? By itself, right? You understand? So what I would do, guys, is I would come over here and I would take a fixed resistor that I know the size of. You know, right now I've got a 10K. What's the color code for a 10K? And then I've got my thermistor. Normally we put sensors inside a circle, and then we would put a T in here. And sometimes they put the little degree symbol. This means it, but this guy is doing this. Now, right now, what we'll do is we'll take our output right here across the thermistor. So I'm going to come over here and I'm going to use a voltmeter. And I'm going to measure the voltage across the thermistor. So let's say +5, which is what I'm going to power it up with. And I'm using a 10K. What's the color code for a 10K? And a brown, black, orange. Now, let's say this guy right here had 10K. Then what would my meter measure? 2.5 volts, which would represent a certain temperature, right? You understand? So let's say I come up here and temperature starts going up. This guy right here starts dropping down. So let's say it goes down to 5K. Now what would my meter measure now? It's supposed to be 5. You can't go up when the resistance is going down. When your resistance goes down, voltage drop is going to do what? In a series circuit, guys, if resistance goes down across a resistor, then so what you're saying, you're telling me a 10K would drop more than a 5K in a series circuit. Yeah, so some of these things you got to what? You got to kind of reason out and understand when your answer's got to be wrong. It's a series circuit, guys. 10K in series with a 5K. Calculate it for me. Where did you learn this at? DZ. Are y'all calculating it for me? We know it's not going to be 2.5. We know it's not going to be 2.5 volts. We know it's going to be less, right? So the voltage drop across the 10K is going to go up, and the voltage drop across the 5K has got to go down, right? Because Kirchhoff's law says what? It says that the voltage drop, the sums of the voltage drops in the series circuit has to equal to the applied voltage. So what we got? $1.6? $1.6? What? Okay, so this guy went down to 1.6 volts. So what did this guy have to go up to? So now I've got a voltage that varies with temperature, right? You understand? Now we can transmit a voltage over a piece of wire, right? And now this means something. So now I got a quantity that I could process with something. If I needed it to act like so this is why the NTCs are the most popular. I've never seen a PTC because I know that I could come over here and I can put the 10K resistor on the bottom, and then I can put my temperature or my thermistor at the top. +5, and let's say it's 5K, and I take my measurement right here. That means this guy here is going to measure 3.4. This guy here is going to measure 1.6. So here, as the temperature goes up, the resistance goes down. This guy's going to drop less. This guy's going to drop more. So if I wanted it to act like a PTC, I just do what? I just put the my fixed resistor on the bottom, or take it across my fixed resistor. So like I said, I've never seen a PTC. I've never seen one. But I can look at Jamico. I've never ordered one. Let me rephrase that. So now we can come up here and we can get a voltage with a change in resistance, right? You understand that? So just about any sensor that changes its resistance with what it measures, we're either going to convert it into a voltage or we're going to convert it into a current. Current's real easy, because what I would do is if I wanted a current, then my current would be down here. So this would be this, and then my sensor would be right there. And now, so the sensor itself, just putting it across a voltage source, I mean a current source, would actually generate either which way we want to send it. Do we want to send it as a current, or do we want to send it as a voltage? And which one do you think is used most of the time? Voltage, yeah. Now the problem is that there's no reference to what 0 equals to. So what I would like to do, when we were sitting at 0 degrees, and Celsius is easier to deal with, then I would need a way to do what? To set a what? 0. Everybody okay with that? So how would we do that? How would I make this thing when it was measuring 0 degrees Celsius? How would I make this voltage right here be 0 degrees? Now we can't use this circuit. We got to come up with another circuit. Yeah, to make the output voltage of my sensor be 0 degrees, show me 0 volts when the thermistor was measuring 0 degrees Celsius. Because it's going to have a resistance, right? You understand that, and the resistance is going to go up. It's going to go down when the temperature goes up. The one we got. So how would I set a 0? Anybody know? Where are we getting all this stuff from? Did y'all learn about the Wheatstone Bridge in D.C.? I hope so. Vaguely. Well, what it is a series parallel circuit, but it's a real neat circuit in that most people draw it like this. Well, that's not exactly true, but this is one way they draw it. Yes, but instead of using diodes, we're using what? Yeah, and that's the way the full wave bridge got its name. Now, what we do is we're going to put our power right here. So let's say this is plus and this is minus. But what we're going to do is we're going to take our output of our sensor right here. Now I'm going to redraw this instead of like I'll draw the bridge. I'm going to put it this direction right here because it's a little easier for me to see and explain. So this is minus. This area would be plus. And I'm going to put a voltmeter right here. And we'll start off just making them all equal to each other. Let's say this is a 10K, this is a 10K, this is a 10K, and this is a 10K. And let's use 10 volts instead of a... So if this is a 10K and this 10K, what voltage would I have right here? And we're going to use this right here as our common. So all our measurements are going to be relative to this. So what would So normally what we have in these sensors is you saw the pressure sensor had a little adjustment on it. So normally what we have is we have the sensing element, which feeds an electronic circuit called a comparator. So when you compare something, what do? You see if they're same or if they're different. So what we can do with this is that's what a comparator would do. So what we do is we set a reference down here, let's say 3 volts, with this pot, or this, I'm sorry, this rheostat. And then when this unit right here gets up to 3 volts or above, then the output would switch. And if it drops down to 3 volts, then the output will switch off. So this is, and all this would be inside our sensor. And then, of course, this would come out, and that would feed my system. So what this does, this allows us to take an analog sensor and convert it into a digital output. Does that make sense? And a lot of these sensors, I have a little threshold adjustment on it, like we saw on that pressure sensor back there, where I could set where it tripped. So this is the basic circuit right here. So the sensing element would be over here. It'd probably be right here somewhere. I'm sorry. Because it's got to be exposed to the outside, right? And this is it. So that's all there is to it. So a lot of your sensors, we'll go back and look at them, and a lot of them have these little calibrations on it, so you can do you can calibrate them. Some of them allow you to actually set the span. So what we can do with this guy is we bring the input of our sensor, and then we'll have one like this, and then we'll have one like this. I need to draw this a little better. So this would come into its own comparator. I got this backwards, guys. Excuse me. And this would go back to the sensor, and then it would go down here to another set. And so we'd have 2 adjustments on these. And then it would also come down and come into this guy. So what we could do is we could set a low, and we could set a what? A high. So what this right here, what would happen is the output would be up here high during a certain range. So we could actually set the range. Does that make sense? So we'll go back here in a minute, and we'll look at the ultrasonic sensor, and we'll see we got 2 adjustments on it, so we can set when it trips on the high side and when it trips on the low side. So what we're doing on the ultrasonic sensor is we're actually measuring the height of something. So if it's got 2 adjustments on it, it means you can set what we call a span, right, between what's true and what's false. And if it's got 1, then all you're going to do is be able to adjust the threshold. So ultrasonic sensors, have you ever seen one of these? How many of y'all have got backup warning on your car where you get close to somebody or something happens? What do you think that is? Ultrasonic. Or when cars are beside you, they let you know. My wife's got little arrows on, Yeah, blind spot warning, yeah, on your mirrors. Those are ultrasonic sensors, right? And somewhere there's an adjustment on those things. Converts ultrasonic sound waves into electrical signals, or vice versa. Measures the time interval, and so we have several things that do that. Radar works exactly the same way. It's just radar is an extremely high frequency. These are in what we call the ultrasonic frequency range, which would be up in the gigahertz. So what it does, it basically sends out pulses, and then it measures the amount of time that it takes for the pulse to come back when it reflects off something. So these guys depends on reflection. So that's what they're doing on our airplanes now. They're trying to make the surfaces that actually absorbs the radar, right? You understand, or reflects it back away from the trans. So these guys can be digital analog. They can be diffused, which means it actually bounces off the device, or it can be direct. Direct means you would have the transmitter and the receiver would be separated, and you do this, so it kind of works like a direct scan. So on that guy, you're blocking the beam. And diffuse is what we see most of all, where it literally comes back and it hits the what? It hits the object, and then it counts at how long it takes to bounce back. And these guys are very precise. I backed my Jimmy into something the other day because I didn't have that warning detector on there. So I got a dent in the back of my Jimmy. So ultrasonics, these are different ways. A lot of times, this is the ultrasonic we've got basically. It's a diffuse type. These are ultrasonic sensors. When they say you had a sonogram, right? That's the ultrasonic sensor. It's actually bouncing off different. Anybody ever had a sonogram? Yeah, I did. I was laid on my back so long that they were scared I was going to get blood clots in my back in the leg, and they checked my main vessels all the way down my leg. So they put that old goop on you, and then yeah, it's a coupling because your skin wants to give and your thing is flat, so they put a goop on you, a gel on you. That's an ultrasonic coupler, so you get a real good coupling between the transmitter and your. And then they push real hard too, guys. So ultrasonic sensors. So let's go back. I think we got an ultrasonic sensor back here. Let's go back and look at it. Put with the time for me. Piezo-resistive. This is solid state, and what we're trying to do is trying to get through most solid state sensors, right? Piezo-resistive. Piezo means pressure. Piezo means it varies its resistance with pressure. So this guy is a solid state sensor that varies its resistance with pressure. Piezo-resistive. So piezoelectric, what would that mean? Generates a voltage with pressure. So that's what your little lighters do now. So now when you press that thing, it pops a piezoelectric crystal and generates an arc. So just about all your cigarette lighters, or if you got a gas grill, or my wife loves candles. But we don't hardly see matches anymore, do we? We see those piezoelectric lighters. So this guy senses pressure. I've got one up here somewhere. This came off a compressor. And this has a span set in it. For normal household compressors or normal compressors, we usually want to cut them off. We let them charge their tanks up to around 100 psi, and then we cut them off at we cut them back on at 70 psi. So that's a piezo-resistive. But it's got a switching circuit in it, right? So these guys measure what? Their resistance with pressure. The threshold's already built into that, though, by the way. And it's got a span, right? Anybody got a compressor? Yeah, that's a good tool to have. That's one of those pieces of equipment that's paid for itself multiple times. I got a welder too. That sucker's paid for itself multiple times. That's what you're looking at right there, by the way, guys. Photoelectric. This should be in chapter 15. So what we're going to do is we'll just touch on this. I know it's almost time to go. Let's look at. I don't know what it is in the old book, but y'all have the new book or you have the old book? Oh, y'all got the old book. Well, it should be in there too. These are photoelectric devices, and the book does a really good job on these. Most of y'all understand light emitting diodes, liquid crystal. Y'all probably seen LCDs, right? Liquid crystals. No, plasma is a gas. Plasma TVs use a gas that changes colors with electricity. Most of your new ones. So this right here uses liquid crystal. We call them LEDs now because liquid crystals, to work, they have to work off reflective light, or they have to be backlit. In the old days, when we had these, when these flat screen monitors came out, we backlit them with a fluorescent bulb, one bulb. So what happened when your one bulb went out? Yeah, you're just out of luck. Mostly now they call them LED displays, but they're liquid crystals, but they're backlit by LEDs, a bunch of LEDs. And now if one of your LEDs goes out, you probably won't even notice it. Yeah. So liquid crystal, these are visual displays, photodiodes. We'll look at those, photoresistors. Have we touched on photoresistors already? Is that this side? Yeah. Photovoltaic cells we've already looked at. Photoelectric transducers, and these are our these are a bunch of our sensors right here: through the beam, retroreflective, and diffused. And are these in your textbook? This might be in chapter 15 because that's what they've done most of their photoelectric at. So how does the light emitting diode work? LED, light emitting diode. First of all, we know it only should conduct in how many directions? One, right? We can either forward bias it or reverse bias it, right? Forward bias it should do what? Come on, right? Reverse bias it should what? Turn off. This is not to know stuff. So we can get this anywhere. We can get photodiodes, LEDs that's anywhere in the light spectrum. The light spectrum runs all the way from infrared up to ultraviolet. And we cannot see infrared and we cannot see ultraviolet, even though they can include those into the light spectrum. So these photoelectric devices, these LEDs, when I flash them at you like this, can y'all see this? Okay, what does that mean? It means it's either it's red or violet. Yeah. Yeah, too fast for your receptors. And of course, we can. This camera up here is taking pictures at a certain rate. We call it a frame rate, so it slows everything down. So that means is I can bring up my camera, and I'm gonna hit a button that's not going to affect and we can literally do what? Yeah, we can see it now. What's that? So we just proved to y'all that it's flashing, right? Huh? And of course, different lights come at different colors, right? Y'all understand that? So different. We call them wavelengths. That would be the frequency, but the frequencies are so high. What they actually calculate is the distance between the distance between that. We call it wavelengths. Y'all understand what I'm saying? Yeah, we see everything in here. Between infrared and ultraviolet, we can see. Anything out of that, we can't see. Right? So this is the way we get colors is we put out what we call, and like I said, light frequencies are so high, these things are way up in the gigahertz, that what we do instead of talking about the frequency, we actually calculate the speed, the actual distance between the, let me see. So these things are traveling like this, right? They're AC. And then what we do is we actually calculate the distance right here. And we call that a wavelength. And in the light spectrum, these are all going to be in what we call, they're going to be in nanometers. So around the 800s, these are reds, right? And then the higher the frequencies, we get into blues and all different types of colors in between those. So the visible light, around 660 nanometers up to about 1550. And this is nothing you're going to be tested on, guys. But you need to understand when we start looking at the rating of LEDs, depending on their color, that's one of the things they're going to give you. They're going to give you the wavelength. Are we okay? And we don't need the formula. Y'all don't need that garbage. Don't need that. So here's LEDs. So all diodes put out photons, but the photons are things that move and produce light, right? You understand that? But the problem is that a regular LED, like made out of silicone or germanium, the photons they put out is a wavelength we couldn't even use anyway, and there's so few of them because of the energy the energy that's developed. So this is why we can't see. This is why they don't worry about regular diodes. They'll put them in a plastic pack because even if they put it in a glass pack or a transparent pack, you couldn't see it anyway, right? So what we're doing is that when these things combine at the junction and these things start bouncing out, then we start emitting these things called photons. And then photons, these are just light energy, right? You understand that? But all diodes do that when these things collide at the junction, right? When these holes do that, they'll emit a photon. So what we're talking about is that LEDs are not made out of silicon and they're not made out of germanium. Most of them are made out of, it's contrary to popular belief, gallium. The color of the lens of an LED does not determine the color. The color is created by the LED itself. The lens only does what? Enhance the colors. Huh? No, the lens just enhances the colors. It's already coming out. And then we can have different lenses. We have what we call a diffuse lens, which basically makes it look like the whole LED is glowing. And then we have I forgot what they call them, but it only comes out one side, right? You understand? So what we dope the gallium with depends on the color, and we've got all types of colors now, guys. Gallium arsenide, gallium arsenide phosphate, gallium phosphate produces these colors, right? You understand that? Okay. So here's all the colors of LEDs we can currently get. And this tells you exactly what they're doped with. You need to know this? No. All you need to understand, number one, is that they're not silicone and they're not germanium, and the VF is going to be greater than 7/10 of a volt because you've got to create more energy to cause those photons to come out, right? That makes sense? So we've got all the way up to what now? We got all the way up to pale white, cool white, and it took them a long time to get here. This gives you the actual wavelengths. So this is the symbol for an LED. Normally we don't put the circle around there, even though it's part of the symbol. But on an LED, the arrows do what? Point out, right? Now, rule of thumb, if you don't have the data sheet, rule of thumb, what we do is we usually use a VF of around 2 volts. What do you mean? No, here's the LED. This is what makes it an LED right here. That's a transistor. That's not. We still call this the cathode. We still call this the anode. And we just show you some of the techniques. Some meters won't check this on the diode scale because of the 2 volts. Some meters won't put out 2 volts. Some meters will. So if you measure a diode with an ohm meter to see if it's good or bad, or to identify the cathode, it might not work on your meter. So that's one thing you probably need to check, is to get an LED, and we'll let y'all do that and let you see if your meter will actually check a diode. If it shows infinity in both directions, it don't mean the LED's bad. It just means what? Your meter might not put out enough voltage to turn the thing on. On these diodes that we're going to be using, what we've got is they're going to be a cap on them like this, and then they're going to have a little lip around on the outside. And what we do is we looked at the lip, just the lip, what we would notice is got a flat side on it. And then the leads are going to be on here, and the flat side would identify the lead, that's the cathode. And then what they'll do is also what they'll do on this is if you look at them, is you'll see one of the leads is shorter than the other. And the short lead identifies the cathode. So here y'all can come up. Y'all need to bring these back up to me. So y'all can look at these. Now the problem is that I think we got enough for everybody. Here we go, Bernard. We do. The problem is you can't depend on this because one of the first things you do when you clip it is you cut the leads off, right? So you'll see a lot of these, even some of these, the leads have been cut off on them, which means now I would have to use this. So basically on these diodes, you got two methods of identifying the cathode. You got the flat side that's on that little rim. Y'all see it? Okay. And then we got one, or you got one lead is shorter than the other. Yeah, on the meter certification. And we need to talk about that. We have to figure out, I don't know what we're going to do about that. Well, they do it in DC because it takes, technically we're supposed to take you through a lecture, and the lecture takes about 4 hours. But we could probably bring you in and let you go through the PowerPoints by yourself and do the labs. And then I could set the test up for you. And when do you need that by? Soon? Well, basically you can let them know that you're going to get it. The meter cert, huh? If they ask you about the meter certification, tell them you're lined up to get it. And then that way, what we'll do is we'll see when Allison is going to give it in her DC class. I think it's nights. Could you do it at night? And let you come in and set in on it and do it. We could do that, no doubt. Anybody in here don't have their meter certification? You don't have it? Well, you would know. You'd had it. Well, no, it depends on when you took DC. It all depends. We hadn't been certified to do it for, I can't remember. Yeah, if you took it at Hoyt, we can't let Willie do it anymore because he can't do the meter certification. But if you took it with Hoyt, it would depend on when you did it. When did we start offering it in DC? I don't know. But I can go. I'm the administrator of the NC3 site, so I could go back and look and see if y'all got it. And if you hadn't, I'll let y'all know. I'll let y'all know when Allison's going to be doing it at nights. And then if y'all can make it out here to get that meter certification on your resume, yeah. I already show y'all one day the certifications that I've got. If you would remember it because this is the certification card right here. So you would be using that Snap-on meter. So odds are, if you were in no, you do it. You have to come over here because this is the only place we got the card. So you had to come over here to do the certification. Yeah, they got a card. Yeah. So we got two cards. We got one on Birmingham campus, and we got one on the. So I'll let y'all know. It's going to be toward the end of the semester though, and let y'all go ahead and get that out of the way because it's free. It don't cost y'all anything, so that's neat. And fluid power, if y'all had fluid power yet, y'all take fluid power yet? Hydraulics, pneumatics, are y'all going to take it? Well, you're gonna get a certification in that too. What? We just got approved for that. This is the only second group we're doing certifications of that. So. No, it's a lecture followed by a certification on their equipment. So the problem we have, and that's one of the reasons why it's free, because they have a lot of sponsors. So what we have is we have sponsors that sponsor the certification. So you have to do what? You have to use their equipment to be certified. But they're also going to do hydraulics this time, guys. We got a new hydraulic trainer. So I can check and see when she's going to do that, if y'all have already had it, and see if y'all could get the hydraulics too. And try to. It'll be toward, all the certifications are toward the end, because you got to know a lot of stuff before you do it, right? So now in fluid power, we can give you a certification in pneumatics and hydraulics. And it's not going to be long where we're going to be able to give you all certification in PLCs, guys. So I'll let you know when we're going to get that. And that'll probably be spring semester though, because we're just now getting the equipment to do it. But we have been certified to do it. We just haven't got the equipment yet. What time is it? Yeah. Yeah, 208 we've only offered twice. It should be. It's a UT 208. Diagnosis, yeah, system diagnosis and troubleshooting. So what we do in that class, guys, is we play around with that line right there. You've already had it, hadn't you, Austin? Nobody's had it in here. Both of them hard. Digital, you're not worried about math. There's really no math. It's all about components, understanding how. Yeah, you'll hook up circuits that you'll take pictures of. You got all these wires coming off of it. You hook circuits up in there that impress people. So y'all seen LEDs all over the place, right? These big old what do they call them? These big old displays that we have now, which is nothing but extremely big monitors. A lot of them just show PowerPoint presentations. So, then regular LEDs. We call these 7-segment LEDs. So what they do is they arrange the LEDs so we can display numbers. These are probably the cheapest ones. Y'all see these all over the place. Y'all see why they're called 7-segment? Yeah, 1, 2, 3, 4, 5, 6, 7. Now they don't count the decimal points. So that would be now what can I do with that? Well, I can display any number, right? Some letters, but not the whole alphabet. We go into these guys right here. If y'all can see this right here, these stars, where they got all types of LEDs. So they got one here, they got one here, 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 here. Yeah, those can do the whole alphabet. And this is basically what your watches and stuff have on them now. Guess what time it is. So this is where we're at. We're looking at light emitting diodes, and we'll come up here and we'll play around with these a little bit. So any questions so far? Hey, your TO208 is